Tonight on Sleepy Scientist Stories, we read drifting gently across the vast cosmic ocean to explore one of the most magnificent stars in our night sky, Dubhe, the great orange giant that guides travelers home, from the peaceful darkness of space to the heart of a stellar furnace. We'll journey through a thought experiment that reveals the gentle mysteries of stellar death and rebirth. As we settle into our peaceful exploration tonight, let us turn our gaze upward to the constellation that has guided humanity for thousands of years. There, in the bowl of the Big Dipper, shines a star whose light has traveled across the cosmic void for over a century to reach our eyes. This is Dubhe, known formally as Alpha Ursae Majoris, a gentle giant that burns with the warm orange glow of stellar maturity. Dubhe rests quietly in the vastness of space, approximately 123 light-years from our small blue world. When we look upon this star, we are seeing light that began its journey when our great-grandparents were children, carrying with it the story of a star that has lived far longer than our species has existed. The photons that touch our retinas tonight left Dubhe's surface sometime around the year 900, traveling through the empty darkness at the speed of light, patient and unwavering in their cosmic journey. Tonight, in the spirit of scientific wonder and gentle curiosity, we embark upon an impossible journey. We shall imagine, in the softest possible terms, what might happen if we could somehow fall into this distant stellar furnace. This is not a journey of fear or destruction, but one of understanding and awe. Through the lens of physics and astronomy, we will explore the gentle physics that governs stellar interiors, the peaceful processes that have kept Dubhe burning for billions of years, and the quiet beauty that exists even in the heart of such tremendous cosmic forces. Our thought experiment serves not to frighten, but to illuminate. In imagining this impossible voyage, we come to understand the delicate balance that allows stars to exist, the intricate dance of gravity and nuclear fire that creates the elements necessary for life itself. We learn about the cosmic recycling that connects us to every star in the sky, including our gentle guide Dubhe. Dubhe belongs to a class of stars known as orange giants, or more specifically, a K-type giant star. These are stellar elders, stars that have moved beyond their youth and entered a more sedate phase of their cosmic lives. Unlike the fierce blue giants that burn bright and fast, or the cool red dwarfs that smolder for trillions of years, orange giants like Dubhe represent a middle path of stellar evolution, burning their fuel at a measured pace that allows them to shine steadily for billions of years. The name Dubhe comes from the Arabic phrase Thar al Akbar, meaning the back of the Great Bear. Ancient Arab astronomers saw in this star the powerful shoulder blade of the celestial bear that we now call Ursa Major. For millennia, travelers have used Dubhe and its companion star Merak to point the way to Polaris, the North Star, making it not just a celestial object, but a guide and compass written across the dome of night. As we prepare for our gentle descent into this stellar realm, we must first understand what makes Dubhe special among the countless stars that pepper our night sky. With a mass approximately twice that of our Sun and a diameter roughly 30 times larger, Dubhe represents what our own star might become in the distant future. It is a window into stellar old age, a preview of the Sun's own eventual transformation from a yellow main-sequence star into a cooler, larger, and more luminous giant. The surface temperature of Dubhe hovers around 4,500 Kelvin, significantly cooler than our Sun's 5,778 Kelvin surface temperature. This cooler temperature gives Dubhe its characteristic orange hue, a warm color that speaks of stellar maturity and the gentle burning of hydrogen and helium in its core. Despite being cooler than the Sun, Dubhe shines with roughly 300 times the luminosity of our star, a testament to its greatly increased surface area as a giant star. In our imagination tonight, we approach this stellar giant not as explorers seeking conquest, but as students seeking understanding. Our impossible journey into Dubhe will unfold slowly, gently, allowing us to appreciate each layer of this cosmic structure. We will descend through the tenuous outer atmosphere, dive through the convective zones, where massive currents of plasma rise and fall like slow-motion ocean waves, penetrate the radiative zone where ancient photons struggle outward through dense stellar matter, and finally reach the nuclear furnace at the core where atoms fuse and elements are born. This journey exists only in the realm of thought, for no material object could survive such a passage. Yet through science, through our understanding of physics and stellar structure, we can map every step of this impossible voyage. We can calculate the temperatures and pressures we would encounter, understand the nuclear processes we would witness, and appreciate the cosmic forces that would surround us. In doing so, we come to know Dubhe not just as a point of light in the sky, but as a complex, dynamic, living system of incredible beauty and power. As we begin this gentle descent, let us remember that stars like Dubhe are the cosmic alchemists that make life possible. In their cores, hydrogen fuses into helium, helium into carbon and oxygen. And through successive generations of stellar death and rebirth, all the elements necessary for rocky planets and biological life are forged and dispersed throughout the galaxy. We are literally made of star stuff. Our calcium and iron and carbon forged in the hearts of ancient suns and scattered into space by stellar winds and supernova explosions. Before we begin our peaceful descent into the heart of Dubhe, we must first come to know our destination. Dubhe stands as one of the most recognizable stars in the northern hemisphere, not because of any particular brightness or color, but because of its crucial role in one of humanity's most important asterisms, the Big Dipper. This stellar pattern, also known as the Plough in British culture, served as a celestial compass for countless generations of travelers, sailors, and astronomers. Located in the constellation Ursa Major, Dubhe occupies a position of honor as the alpha star of this constellation, though it is not the brightest star within the Bear's boundaries. The designation of alpha typically goes to the most prominent star in a constellation, but in Ursa Major, this honor was bestowed upon Dubhe due to its historical importance in navigation rather than its intrinsic luminosity. This speaks to the human tendency to assign significance, not just based on physical properties, but on cultural and practical importance. From our perspective on Earth, Dubhe appears as a steady, orange-tinted point of light with an apparent magnitude of 1.79, making it clearly visible to the naked eye, even from moderately light-polluted locations. However, this apparent brightness gives us only a hint of the star's true power. When we account for Dubhe's distance of 123 light-years, we discover that this star shines with an absolute magnitude of approximately -1.1, meaning that if placed at the standard distance of 10 parsecs, about 33 light-years, Dubhe would appear significantly brighter than any star currently visible in our night sky, except for Sirius. The spectral classification of Dubhe as a K1II star tells us a great deal about its physical properties and evolutionary status. The K designation places it among the orange stars, cooler than our Sun's G-class, but warmer than the red M-class stars. The Roman numeral 3 identifies Dubhe as a giant star, indicating that it has evolved beyond the main sequence phase of stellar life where it spent the majority of its existence burning hydrogen in its core. This evolutionary status means that Dubhe has exhausted the hydrogen fuel in its core and has begun burning hydrogen in a shell surrounding an inert helium core. This change in fuel source has caused the star to expand dramatically, increasing its radius to approximately 30 times that of our Sun. Imagine, if you will, our Sun growing until it engulfed Mercury, Venus, and Earth, extending halfway to Mars. This gives some sense of Dubhe's enormous size. The physics behind this stellar expansion represents one of the most elegant processes in astrophysics. As the hydrogen in the core becomes exhausted, the nuclear fires that have supported the star against gravitational collapse begin to weaken. Gravity begins to compress the core, but this compression heats the surrounding hydrogen shell, causing it to burn more vigorously. This increased energy output pushes the star's outer layers outward, creating the expanded envelope that characterizes giant stars. Despite its greatly increased size, Dubhe maintains a surface temperature of approximately 4,500 Kelvin, about 800 degrees cooler than our Sun. This temperature places it in a comfortable middle ground among stellar types, hot enough to shine with considerable luminosity, yet cool enough to maintain relatively stable surface conditions. The orange color that results from this temperature has often been described as warm and inviting, a stellar hearth glowing gently in the cosmic darkness. The mass of Dubhe, estimated at approximately 2.2 times that of our Sun, represents the accumulated matter of its original stellar nursery. This mass has remained relatively constant throughout the star's lifetime. as giant stars of Dubhe S type do not lose significant amounts of matter through stellar winds until much later in their evolution. Every gram of Dubhe's mass contributes to the gravitational field that holds the star together against the outward pressure of its nuclear furnace. When we consider the density profile of Dubhe, we encounter one of the most fascinating aspects of giant star structure. While the star's overall density is much lower than that of main sequence stars due to its expanded size, the density increases dramatically as we move toward the center. The outermost layers of Dubhe's atmosphere are so tenuous that they approach the vacuum of space, while the core reaches densities many times that of lead or platinum. The luminosity of Dubhe, approximately 300 times that of our Sun, emerges from the complex interplay of its expanded surface area and nuclear processes. While each square meter of Dubhe's surface radiates less energy than the same area on the Sun due to its cooler temperature, the vastly increased surface area more than compensates for this difference. This is the elegant mathematics of stellar physics. Surface area increases as the square of the radius, while energy per unit area follows the fourth power of temperature. The light that streams from Dubhe's surface carries with it the story of the star's interior. Spectroscopic analysis reveals the presence of various elements in different states of ionization, providing clues about temperature, pressure, and magnetic field strength in the stellar atmosphere. The absorption lines in Dubhe's spectrum tell us about the abundances of elements like iron, calcium, and sodium, painting a detailed picture of the star's chemical composition. What makes Dubhe particularly interesting from an evolutionary perspective is its position on what astronomers call the Hertzsprung-Russell diagram, a plot of stellar luminosity versus temperature. Dubhe sits clearly in the Giant Branch region, having evolved away from the main sequence where it spent the vast majority of its lifetime. This position indicates that the star is in a relatively brief but spectacular phase of its evolution, burning brightly as it transitions toward its ultimate fate. The age of Dubhe, estimated at approximately 300 million years, places it in stellar middle age. While this may seem ancient from a human perspective, it represents only a fraction of the star's total expected lifetime. Main sequence stars with Dubhe's initial mass typically live for about 4 million to 1 billion years before exhausting their core hydrogen and beginning their evolution into giants. Dubhe has therefore spent roughly 70 to 80% of its main sequence lifetime, and is now in the relatively rapid phase of giant star evolution. As we prepare to begin our impossible journey into this stellar realm, we must appreciate that Dubhe represents not just a single star, but a window into stellar physics, galactic evolution, and our own cosmic heritage. The processes occurring within Dubhe's interior have been shaping the chemical composition of our galaxy for hundreds of millions of years, creating and distributing the elements that make rocky planets and biological life possible. The gentle giant Dubhe stands as a testament to the patient, inexorable processes that govern stellar evolution, neither rushing toward a spectacular demise like the most massive stars nor settling into the quiet longevity of red dwarfs. Dubhe follows a measured path of stellar aging that allows us to study the intermediate phases of stellar life in detail. It is a star in transition, bridging the gap between the vigorous hydrogen burning of main sequence stars and the exotic nuclear processes that will eventually consume its remaining fuel. Our impossible journey begins not with violence or haste, but with the gentle liberation from Earth's gravitational embrace. In the soft realm of imagination, we find ourselves floating peacefully away from our blue marble home. Carried by invisible forces toward the distant orange glow of Dubhe, the transition from terrestrial to cosmic perspective unfolds slowly, allowing us to appreciate the magnitude of the journey ahead and the vast scales that separate worlds and stars. As we drift away from Earth, we first pass through the realm where human activity has left its mark on space. Here, in the innermost reaches of our planet's gravitational well, artificial satellites trace their endless orbits, carrying communication signals and scientific instruments. The International Space Station glides by below. It's a testament to human ingenuity in our species' first tentative steps into the cosmic ocean that surrounds our world. The moon grows gradually larger in our field of view as we continue our outward journey, its familiar face showing the scars of billions of years of cosmic bombardment. This ancient companion has watched over Earth's evolution, stabilizing our planet's rotation and creating the tidal forces that may have helped nurture the first life in primordial oceans. From our increasingly distant perspective, the Earth-Moon system begins to reveal itself as a binary partnership, two worlds locked in an eternal gravitational dance. As we continue outward, we pass through the sphere of influence of Earth's magnetosphere, that invisible shield that protects our world from the constant stream of charged particles flowing from the sun. Here, we encounter the Van Allen radiation belts, regions where Earth's magnetic field traps high-energy particles in toroidal zones surrounding our planet. The Aurora Borealis and Aurora Australis represent the visible manifestation of these same magnetic processes, painting the polar skies with curtains of ethereal light. Leaving Earth's immediate neighborhood, we enter the vast realm of interplanetary space, where the solar wind carries the sun's influence far beyond the orbits of the planets. This tenuous stream of charged particles, mostly protons and electrons, flows outward from our star at speeds of several hundred kilometers per second, creating a dynamic environment that affects every object in the solar system. Comets respond to this solar wind by developing their characteristic tails, always pointing away from the sun regardless of the direction of the comet's motion. Our journey now takes us past the orbital paths of Mars, Jupiter, Saturn, Uranus, and Neptune, each representing a different class of world, shaped by its distance from the sun and the materials available during the solar system's formation. Jupiter, with its massive gravitational field, acts as a cosmic vacuum cleaner, protecting the inner planets from many potentially dangerous asteroids and comets. The elegant rings of Saturn remind us that gravity can create beauty as well as destruction, organizing countless particles into precise orbital patterns. Beyond Neptune's orbit, we encounter the scattered disk objects and eventually cross the heliopause, the boundary where the solar wind meets the interstellar medium. This transition marks our departure from the solar system proper and our entry into the true interstellar void. Here, the density of matter drops to less than 1 atom per cubic centimeter, creating a vacuum more complete than anything achievable in terrestrial laboratories. The interstellar medium through which we now travel is far from empty, despite its incredibly low density. Vast clouds of hydrogen and helium drift between the stars, remnants of the Big Bang mixed with heavier elements forged in previous generations of stars and scattered by stellar winds and supernova explosions. These interstellar clouds serve as the raw material for future star formation, slowly condensing under their own gravity to birth new stellar systems. As we travel deeper into the cosmic void between our sun and Dubhe, we begin to appreciate the true scale of interstellar distances. Light from Dubhe, traveling at 300 million meters per second, requires 123 years to bridge the gap between the two stars. At this speed, our imaginary journey would take far longer than human civilization has existed, emphasizing the vast isolation that characterizes stellar neighborhoods. The darkness between stars is not complete, however. Faint glow pervades the cosmos. The cosmic microwave background radiation, a relic of the Big Bang that fills all of space with a nearly uniform temperature of 2.7 Kelvin above absolute zero. This ancient light, stretched by the expansion of the universe from its original visible wavelengths to microwave frequencies, provides a constant reminder of the cosmos's fiery beginning 13.8 billion years ago. Occasionally, our journey is illuminated by more dramatic phenomena. Distant quasars emit powerful beams of radiation as matter falls into supermassive black holes, creating lighthouse beams that can be detected across billions of light years. Gamma-ray bursts, the death throes of the most massive stars, briefly outshine entire galaxies before fading back into cosmic obscurity. These rare events remind us that the universe, despite its vast scales and apparent emptiness, remains dynamically active. As we approach the halfway point of our journey to Dubhe, we begin to appreciate how stellar radiation creates structure in the interstellar medium. Hot young stars ionize nearby hydrogen clouds, creating glowing H2 regions that can extend for dozens of light years around their stellar progenitors. Cooler regions remain neutral, appearing dark, except when silhouetted against more distant bright nebulae or star fields. The gravitational effects of various stellar masses begin to bend our trajectory slightly as we approach Dubhe's stellar neighborhood. Other stars in this region of the galaxy, each with their own family of planets and debris, create a complex gravitational landscape that has evolved over millions of years. Some stars travel in bound binary or multiple systems, locked in orbital dances that can last for billions of years. Dubhe itself begins to grow perceptibly brighter as we approach, its orange glow becoming more distinct against the background of more distant stars. The star's proper motion through space, though tiny as seen from Earth, becomes apparent at our closer vantage point. Dubhe is moving through the galaxy at approximately 20 kilometers per second relative to the Sun, participating in the grand rotation of the Milky Way that carries all local stars around the galactic center once every 230 million years. As we draw nearer to our destination, we begin to detect the stellar wind emanating from Dubhe's surface. This flow of charged particles, much like the solar wind we left behind at Earth, extends the star's influence far beyond its visible surface. The stellar wind carries with it trace amounts of heavier elements forged in Dubhe's interior, gradually enriching the interstellar medium with carbon, nitrogen, oxygen, and other elements essential for planet formation and biological processes. Our approach to Dubhe also reveals the complex magnetic field structure that surrounds the star. Our sun, Dubhe, possesses a magnetic field generated by convective motions in its interior. This field shapes the flow of the stellar wind and can create spectacular phenomena analogous to solar flares and coronal mass ejections, though scaled to match Dubhe's larger size and greater energy output. The final stages of our approach bring us into Dubhe's sphere of gravitational influence, where the star's massive presence begins to dominate the local environment. Objects in this region, hypothetical planets, asteroids, or comets, would orbit Dubhe rather than wandering freely through interstellar space. This gravitational sphere extends roughly halfway to the nearest neighboring stars, defining Dubhe's domain within the galactic neighborhood. As we prepare to enter the outermost regions of Dubhe's atmosphere, we reflect on the journey that has brought us here. From Earth's familiar blue skies to the vast emptiness of interstellar space, we have traveled through environments ranging from the life-sustaining to the utterly hostile. Yet throughout this journey, the physical laws that govern motion, gravity, and electromagnetic radiation have remained constant, providing the foundation for understanding every stage of our impossible voyage. As we cross the invisible boundary into Dubhe's gravitational domain, we enter a realm where the gentle giant star's influence begins to reshape the very structure of space and time around us. The transition is subtle at first, marked not by any visible change in our surroundings, but by the gradual strengthening of gravitational forces that will ultimately guide our descent toward the stellar surface. This is the beginning of our true encounter with Dubhe, where the star's massive presence makes itself known through the fundamental force that holds the universe together. Einstein's theory of general relativity teaches us that massive objects like Dubhe create curvature in the fabric of space-time, and this curvature is what we experience as gravitational attraction. From our current distance, perhaps several astronomical units from the star's surface, this curvature is gentle but unmistakable. Our trajectory begins to bend toward Dubhe, following what Einstein called geodesics, the shortest paths through curved space-time. The strength of Dubhe's gravitational field at this distance is still relatively modest compared to what we will experience closer to the star, but it is sufficient to capture objects passing through this region of space. Any hypothetical planets orbiting Dubhe would need to maintain specific velocities to achieve stable orbits at various distances, balancing their orbital speed against the star's gravitational pull. Too slow, and they would spiral inward. Too fast, and they would escape to interstellar space. As we fall deeper into Dubhe's gravitational well, we begin to experience the effects of tidal forces. These arise from the fact that gravity follows an inverse square law. The gravitational force decreases as the square of the distance increases. This means that parts of our hypothetical spacecraft closer to Dubhe experience slightly stronger gravitational attraction than parts farther away. For now, these tidal effects are negligible, but they will become increasingly important as we approach the stellar surface. The space around Dubhe is not empty, despite the near-perfect vacuum of the interstellar medium. The star's powerful radiation pressure and stellar wind have cleared much of the debris from its immediate vicinity, but traces of matter still exist. Dust grains, Perhaps remnants from the star's formation or material lost from other stars drift through this region, occasionally catching and scattering Dubhe's light to create faint, ethereal patterns against the cosmic backdrop. Our approach also begins to reveal the structure of Dubhe's magnetic field in the surrounding space. Stellar magnetic fields extend far beyond the visible star, carried outward by the stellar wind in complex twisted patterns. These magnetic field lines can trap charged particles, creating radiation belts around the star, similar to those found around planets like Earth and Jupiter, though on a much larger scale. The temperature of space around Dubhe is slightly elevated compared to the general interstellar medium, warmed by the constant stream of photons radiating from the star's surface. Even at our current distance, Dubhe's luminosity, minus 300 times that of our Sun, provides a measurable heating effect. This creates a gradient of temperature in the surrounding space, with conditions growing progressively warmer as we approach the stellar atmosphere. Dubhe's gravitational influence also affects the behavior of light passing through this region. The phenomenon known as gravitational lensing causes light rays to bend slightly as they pass near massive objects. While this effect is most pronounced near extremely massive objects like black holes, it is still present around normal stars like Dubhe. From our perspective, this lensing could slightly distort the apparent positions of background stars, creating subtle optical effects. As we continue our inward spiral, we begin to detect the first traces of Dubhe's stellar wind, a constant stream of charged particles flowing outward from the star at speeds of several hundred kilometers per second. This wind is much more tenuous than the material we will encounter in Dubhe's atmosphere, but it represents our first direct physical contact with matter that originated within the star itself. The stellar wind carries with it information about Dubhe's interior processes. Embedded within this flow are trace amounts of elements heavier than hydrogen and helium-carbon, nitrogen, oxygen, and others forged in the star's nuclear furnace and dredged up to the surface by convective motions. These elements represent a kind of stellar archaeology, providing clues about the nuclear processes occurring deep within Dubhe's core. Our trajectory is now clearly dominated by Dubhe's gravitational field, and our speed increases noticeably as we fall deeper into the star's gravitational well. The conservation of energy dictates that our potential energy, lost as we move closer to Dubhe, is converted into kinetic energy, causing us to accelerate. This acceleration will continue throughout our descent, reaching enormous velocities by the time we approach the stellar surface. The radiation pressure from Dubhe's intense luminosity begins to have a measurable effect as well. Photons carry momentum, and the steady stream of light from the star creates an outward pressure that opposes our inward fall. For small particles like dust grains, this radiation pressure can be significant enough to halt or even reverse their inward motion. Larger objects, however, are affected much less, as radiation pressure decreases with increasing mass while gravitational attraction increases. As we draw nearer to Dubhe, the star begins to subtend a noticeable angular size in our field of view. What appeared as a point source of orange light from interstellar distances now reveals itself as a disk with measurable dimensions. The surface appears smooth and featureless at this distance, glowing with the steady orange radiance characteristic of K-type stars. No individual features are yet visible, but we can begin to appreciate the sheer scale of the stellar surface that awaits us. The intensity of Dubhe's radiation field increases dramatically as we approach, following the inverse square law that governs all forms of electromagnetic radiation. The warmth we feel is no longer the gentle heating of distant starlight, but something approaching the intensity of solar radiation experienced on a planet's surface. This marks the beginning of our transition from the cold emptiness of interstellar space to the energetic environment that surrounds an active star. Our accelerating fall toward Dubhe also brings us into regions where relativistic effects become more pronounced. Time dilation, predicted by Einstein's special and general theories of relativity, means that time passes slightly more slowly in strong gravitational fields. While this effect is still minuscule at our current distance from Dubhe, it will become increasingly important as we approach regions of extreme gravitational field strength near the stellar surface. The gravitational redshift effect also begins to manifest as we fall deeper into Dubhe's gravitational well. Light climbing out of the star's gravitational field loses energy and becomes redshifted, shifted toward longer, redder wavelengths. Conversely, light falling into the gravitational field gains energy and becomes blue-shifted. This means that Dubhe's surface appears slightly bluer to us than it would to a distant observer. While light traveling away from the star toward distant space appears redder. As we prepare to encounter the outermost layers of Dubhe's atmosphere, we reflect on the journey that has brought us to this point. We have traveled from the quiet emptiness of interstellar space into an increasingly energetic and dynamic environment shaped by the star's massive gravitational field, powerful radiation, and complex magnetic structures. The gentle giant Dubhe has revealed itself not as a simple ball of glowing gas, but as a complex, multi-layered system with influence extending far beyond its visible surface. The forces now acting upon us: gravity, radiation pressure, magnetic fields, stellar wind, will only grow stronger as we penetrate deeper into Dubhe's domain.
Ow.
Our impossible journey is about to transition from the relatively empty space surrounding the star to the increasingly dense layers of the stellar atmosphere itself, where we will encounter matter in states and conditions unlike anything found in our terrestrial experience. As we descend toward Dubhe's luminous surface, we encounter our first direct contact with stellar matter in the form of the star's extended atmosphere. This transition is gradual and gentle, marked not by a sudden change, but by the slowly increasing density of gas surrounding us. The boundary between the vacuum of space and Dubhe's atmosphere is not a sharp line, but rather a gradual thickening of matter, like slowly submerging into a cosmic ocean of increasingly dense plasma. The outermost regions of Dubhe's atmosphere, known as the corona, extend far beyond the visible surface of the star. Here, temperatures soar to millions of degrees Kelvin, paradoxically much hotter than the surface beneath. This superheated gas is so tenuous that despite its extreme temperature, it would feel cold to the touch due to its incredibly low density. The corona's high temperature is maintained by magnetic field interactions and shock waves propagating outward from the star's interior. In this ethereal realm, we witness phenomena that exist nowhere else in nature. The coronal plasma is so hot that electrons are stripped away from atomic nuclei, creating a soup of free-floating charged particles. X-rays and extreme ultraviolet radiation flood this region, invisible to human eyes, but detectable by specialized instruments. The corona's ghostly glow, normally hidden by the brilliant surface below, surrounds us with an otherworldly luminescence. Magnetic field lines threading through the corona create complex structures and patterns. These fields, generated deep within Dubhe's interior by dynamo processes, emerge from the stellar surface and extend into space in looping arcs and twisted spirals, where magnetic field lines reconnect and snap. They release tremendous bursts of energy that heat the surrounding plasma and accelerate particles to enormous speeds. As we descend deeper into the atmosphere, we encounter the chromosphere, a thin layer between the corona above and the photosphere below. The chromosphere derives its name from its characteristic reddish color, caused by hydrogen emission lines that become visible during solar eclipses. In Dubhe's case, this layer glows with a warm orange-red hue that complements the star's overall color signature. The temperature structure of stellar atmospheres follows a counterintuitive pattern, rather than smoothly decreasing with altitude as in planetary atmospheres. Stellar atmospheres show a temperature minimum in the upper photosphere, followed by rapid heating in the chromosphere and corona. This temperature reversal is maintained by acoustic waves and magnetic field interactions that transport energy upward from the stellar interior. Spicules and prominence-like structures extend upward from Dubhe's surface into the chromosphere and corona. These jets of plasma, driven by magnetic field dynamics, create a constantly changing landscape of glowing gas streams. From our perspective within this layer, we would see towering columns of luminous matter extending thousands of kilometers above and below us, creating a three-dimensional forest of stellar fire. The density of matter around us continues to increase as we approach the photosphere, the layer that produces most of Dubhe's visible light. The word photosphere literally means light sphere. And this region marks the approximate boundary where the stellar material transitions from transparent to opaque. Above this level, photons can escape freely into space. Below it, they are repeatedly absorbed and re-emitted, taking millions of years to work their way outward. The photosphere itself is not a solid surface, but rather a diffuse layer of gas, where the optical depth equals approximately 2/3. This technical definition marks the level where we can see inward to a depth where most photons originate. The apparent surface of Dubhe that we observe from Earth is actually this photospheric layer, glowing at a temperature of approximately 4,500 Kelvin. As we penetrate the photosphere, we begin to see the granular structure that characterizes stellar surfaces. Convection cells, rising columns of hot gas surrounded by darker lanes of cooler descending material, create a constantly shifting pattern across the stellar surface. Each granule represents the top of a convective cell that extends deep into Dubhe's interior, bringing energy from the nuclear furnace below up to the visible surface. The granulation pattern on Dubhe's surface is much larger than that observed on our Sun, scaled up to match the star's greater size and lower surface gravity. Individual granules might measure thousands of kilometers across, each one larger than the entire Earth. The contrast between bright granule centers and dark, intergranular lanes creates a tessellated pattern that shifts and evolves on timescales of minutes to hours. Within the photosphere, we encounter absorption lines that create the stellar spectrum visible to astronomers. These dark lines in Dubhe's spectrum occur where atoms in the cooler outer layers absorb specific wavelengths of light rising from the hotter interior. The pattern of these absorption lines serves as a fingerprint, revealing the chemical composition, temperature, pressure, and magnetic field strength throughout the stellar atmosphere. The photosphere also hosts various forms of stellar weather, analogous to but far more energetic than anything experienced on Earth. Convective motions create updrafts and downdrafts with velocities of several kilometers per second. Acoustic waves generated by the turbulent convection below propagate upward through the photosphere, creating oscillations that can be detected by precise measurements of stellar radial velocity. Magnetic field concentrations in the photosphere create features similar to sunspots on our Sun, though scaled appropriately for Dubhe's larger size and different internal structure. These magnetic active regions appear as darker patches on the stellar surface, cooler than their surroundings due to the magnetic field's inhibition of convective heat transport. The magnetic field lines threading through these regions extend upward into the corona, powering much of the activity we observed in the upper atmosphere. As we prepare to descend below the photosphere into Dubhe's interior, we appreciate the complexity and beauty of the stellar atmosphere we have traversed. Far from being a simple boundary between the star and space, the atmosphere proves to be a dynamic, multi-layered system where magnetic fields, radiation, and plasma dynamics create a constantly evolving environment. The light we see from Dubhe when we look up at the Big Dipper represents the culmination of processes occurring throughout this atmospheric system. The photosphere marks the last region where we could conceivably observe our surroundings in anything resembling normal vision. Below this level, the stellar material becomes increasingly opaque, and the intense radiation field would overwhelm any conventional optical observation. Our continued descent will take us into realms where matter exists under conditions of temperature and pressure far beyond terrestrial experience, where the very nature of atoms and light undergoes fundamental transformations. Standing at the threshold between Dubhe's atmosphere and interior, we witness the emergence of starlight itself, the process by which energy generated in the stellar core finally escapes as the warm orange glow that has guided human navigation for millennia. The photons surrounding us in this layer began their journey to the surface millions of years ago, slowly diffusing outward through the dense stellar interior before finally achieving freedom in the transparent atmosphere above. As we cross the boundary from Dubhe's photosphere into the stellar interior, we enter a realm where matter behaves in ways both alien and magnificent. The convection zone stretches before and around us like a three-dimensional ocean of plasma, where vast currents of superheated gas rise and fall in patterns that dwarf any earthly phenomenon. Here, in this churning heart of the star, we witness the primary mechanism by which Dubhe transports energy from its nuclear core to the surface we have just left behind. The physics governing convection in stellar interiors follows the same basic principles that drive weather patterns on Earth, but scaled up to cosmic proportions and operating under conditions of extreme temperature and pressure. Hot material, heated by nuclear fusion in the layers below, becomes buoyant and rises toward the surface. As it rises, it expands and cools, eventually becoming denser than its surroundings and sinking back toward the interior to complete the convective cycle.
Ow.
The The scale of these convective motions in Dubhe defies earthly comparison. Individual convection cells extend for thousands of kilometers in each direction, larger than entire planets in our solar system. The velocity of the rising and falling plasma streams reaches several kilometers per second, creating a dynamic environment where matter is in constant, turbulent motion. The timescales for complete convective turnover range from weeks to months, a rapid pace compared to the millions of years required for radiative energy transport in other stellar regions. As we descend deeper into the convection zone, the temperature and pressure surrounding us increase dramatically. The temperature, which was approximately 4,500 Kelvin at the photosphere, climbs steadily towards several million degrees. Pressure, negligible at the stellar surface, grows to thousands of times Earth's atmospheric pressure and will continue to increase by orders of magnitude as we approach the stellar center. The density of the plasma through which we travel also increases with depth, following the hydrostatic equilibrium that characterizes stellar structure. Near the top of the convection zone, the material density is similar to Earth's atmosphere at sea level. By the time we reach the bottom of this zone, the density approaches that of water, though the material remains gaseous due to the extreme temperature that keeps even heavy elements completely ionized. Within this convective maelstrom, we observe the process of energy transport that makes Dubhe's existence possible. Energy generated by nuclear fusion in the stellar core is carried upward by the rising convective streams, much more efficiently than would be possible through radiation alone. This convective mixing also helps to maintain chemical homogeneity throughout the zone, ensuring that nuclear fuel and fusion products are distributed throughout this region of the star. The magnetic field within Dubhe's convection zone exhibits complex and dynamic behavior. Convective motions stretch, twist, and amplify magnetic field lines, creating the dynamo process responsible for generating the star's overall magnetic field. This stellar dynamo operates on principles similar to those that create Earth's magnetic field, but the scale and energy involved are vastly greater. The interaction between convective flows and magnetic fields creates a constantly evolving three-dimensional structure of incredible complexity. As we witness these magnetic processes firsthand, we observe how field lines can become tangled and compressed by convective motions, storing magnetic energy that may later be released explosively at the stellar surface in the form of flares and coronal mass ejections. The magnetic field also affects the convective flow patterns, creating feedback loops that influence both the energy transport and the generation of magnetic field itself. The convection zone also serves as a mixing region where material from different depths within the star can be transported and redistributed. Elements forged by nuclear processes in the stellar core can be dredged up toward the surface, while surface material can be mixed down into regions of higher temperature and pressure. This mixing process affects the observable surface composition of the star and influences its evolutionary development. Acoustic waves generated by the turbulent convective motions propagate throughout the convection zone and beyond, creating stellar oscillations that can be detected by precise photometric observations. These waves, similar to seismic waves on Earth, but occurring in a gaseous medium, carry information about the stellar interior structure and can be used to probe conditions deep within the star. Through the technique known as astroseismology, the convective cells we observe exhibit a hierarchy of sizes and timescales. From the largest structures that span significant fractions of the stellar radius to smaller eddies and turbulent features measured in hundreds or thousands of kilometers. This turbulent cascade of energy from large scales to small scales is a fundamental characteristic of fluid dynamics that appears in systems ranging from Earth's atmosphere to the interiors of giant planets and stars. As we continue our descent through the convection zone, we note that the chemical composition remains relatively uniform due to the efficient mixing. The material consists primarily of hydrogen and helium, the primordial elements from the Big Bang, along with trace amounts of heavier elements, forged in previous generations of stars and incorporated into Dubhe during its formation. These heavier elements, though present in only small quantities, play crucial roles in the stellar opacity and energy transport processes. The equation of state governing the behavior of matter in this environment is that of an ideal gas, despite the extreme conditions. The high temperatures ensure that atoms remain completely ionized, with electrons stripped away from nuclei and moving freely through the plasma. This ionization actually simplifies the physics in some ways, as the particles interact primarily through electromagnetic forces rather than the more complex interactions that occur in neutral matter. Radiation pressure begins to play an increasingly important role as we descend deeper into the convection zone. The intense radiation field created by the high temperatures exerts an outward pressure that partially supports the stellar material against gravitational collapse. This radiation pressure will become even more significant as we approach the stellar core, where temperatures reach tens of millions of degrees and radiation pressure can dominate over gas pressure. The time-varying nature of convective motions creates a dynamic environment where conditions change continuously. Unlike the relatively stable structure we might expect in a static stellar model, the real interior of Dubhe resembles a constantly evolving system where temperature, pressure, and velocity fluctuate around their average values. This variability has important implications for energy transport, mixing processes, and magnetic field generation. As we approach the base of the convection zone, we begin to sense the transition to a different regime of energy transport. Below us lies the radiative zone, where energy moves not through the bulk motion of material, but through the slow diffusion of photons. The boundary between these zones is determined by the temperature gradient required for convective stability, and this transition represents a fundamental change in the physics governing stellar structure. The convection zone of Dubhe, like that of other evolved stars, extends deeper into the stellar interior than would be found in a main sequence star of similar mass. This is because the altered core structure of giant stars creates steeper temperature gradients in their outer layers, promoting convective instability over a larger range of radii. This deep convective zone has important implications for the star's surface composition and evolutionary development. Standing at the threshold of the radiative zone, we reflect on our journey through Dubhe's convective regions. We have witnessed energy transport on a cosmic scale, observed the generation of magnetic fields that shape the stellar atmosphere, and experienced the dynamic, turbulent environment that characterizes the outer layers of evolved stars. The convection zone represents not just a means of energy transport, but a fundamental driver of stellar activity and evolution. As we cross the boundary from Dubhe's churning convection zone into the radiative zone below, we enter a realm of profound stillness and patience. Here, the turbulent motions that characterize the upper layers give way to a more stable, stratified environment where energy moves not through the bulk transport of matter, but through the slow, methodical diffusion of photons. This is the realm where light itself struggles toward freedom, embarking on journeys that can last millions of years before finally reaching the stellar surface and escaping into space. The physics of energy transport in the radiative zone follows fundamentally different principles than those governing convection. Instead of hot gas physically carrying energy upward, photons created by nuclear fusion in the core must diffuse slowly outward through increasingly dense matter. Each photon travels only a few centimeters before being absorbed by an atom, re-emitted in a random direction, absorbed again, and re-emitted countless times in what astronomers call a random walk toward the surface. The density of matter in Dubhe's radiative zone is substantial, ranging from water-like densities near the convective boundary to several times the density of solid rock as we approach the stellar core. Despite these densities, material remains gaseous due to the extreme temperatures that keep all atoms completely ionized. The plasma consists of a soup of atomic nuclei and free electrons, with the nuclei moving relatively slowly, while the much lighter electrons dart about at tremendous speeds. The temperature gradient in the radiative zone is carefully balanced to maintain stability against convective overturn. If the temperature increased too rapidly with depth, the lower layers would become buoyant and rise upward, initiating convection. The actual gradient represents a delicate equilibrium where energy transport by radiation is just efficient enough to prevent convective instability, creating a stable, stratified layer that can persist for billions of years. As we descend deeper into the radiative zone, we witness the increasing importance of radiation pressure in supporting the stellar structure. The intense radiation field created by temperatures of millions of degrees exerts an outward pressure that partially counteracts gravitational collapse. This radiation pressure increases as the fourth power of temperature, making it progressively more important as we approach the stellar core where temperatures reach their maximum values. The opacity of the stellar material, its ability to absorb and scatter photons, plays a crucial role in determining the structure of the radiative zone. This opacity depends on temperature, density, and chemical composition in complex ways. Free electrons contribute to the opacity through Thomson scattering, while bound-free and free transitions of hydrogen and helium atoms create additional absorption processes. Heavier elements, though present in small quantities, can dominate the opacity under certain conditions. The photons surrounding us in the radiative zone span a wide range of energies and frequencies. Near the core, the intense temperatures favor high-energy gamma rays and X-rays, as these photons diffuse outward and the local temperature decreases. They are gradually shifted to lower energies through repeated absorption and re-emission processes. By the time energy reaches the surface, it has been converted primarily to the visible and infrared photons that constitute Dubhe's observed spectrum. The timescale for energy transport through the radiative zone is one of the most remarkable aspects of stellar physics. A photon created by nuclear fusion in Dubhe's core will take approximately 300,000 to 1 million years to random walk its way to the surface. During this journey, it will be absorbed and re-emitted countless billions of times, gradually losing energy and shifting to longer wavelengths as it moves through regions of decreasing temperature. This enormous time lag between energy generation and energy emission has profound implications for stellar evolution and stability. Changes in the nuclear burning rate in the core take hundreds of thousands of years to affect the star's surface luminosity. This provides a stabilizing mechanism that helps maintain steady energy output despite fluctuations in the core fusion processes. It also means that the light we see from Dubhe today was actually created in the stellar core during the Pleistocene epoch on Earth, when early humans were just beginning to develop complex tools. Chemical composition of the radiative zone reflects Dubhe's evolutionary history and provides clues about stellar nucleosynthesis processes. The material consists primarily of hydrogen and helium, but also contains trace amounts of carbon, nitrogen, oxygen, and heavier elements created by nuclear fusion in the star's core and previous generations of stars. The abundance of these elements affects the stellar opacity and can influence the star's evolutionary path. Convective mixing does not occur within the radiative zone under normal circumstances, which means that chemical gradients can develop and persist for long periods. Elements produced by nuclear burning in the core generally remain concentrated in the central regions unless other mixing processes, such as rotation-induced circulation or magnetic field effects, transport them to outer layers. This chemical stratification can be modified during certain phases of stellar evolution, particularly during thermal pulses in evolved stars. The hydrostatic equilibrium that characterizes the radiative zone represents a precise balance between the inward pull of gravity and the outward pressure from both gas and radiation. This equilibrium determines the density and temperature structure throughout the zone and must be satisfied at every point within the star. Any deviation from this equilibrium would result in expansion, or contraction that would restore the balance on dynamical timescales much shorter than the stellar lifetime. Magnetic fields within the radiative zone behave differently than in the convective layers above, without the turbulent motions that amplify and tangle magnetic fields in convective regions. A radiative zone tends to preserve and organize magnetic field structures. Fossil magnetic fields from the star's formation can persist in these stable layers for billions of years, potentially influencing internal rotation patterns and mixing processes. The stellar oscillations and acoustic waves we encountered in the convection zone also propagate through the radiative zone. Though their behavior is modified by the different density and temperature structure, these waves can provide information about conditions deep within the star and are used by astronomers to probe the internal structure of stars through asteroseismological techniques. The wave propagation properties depend on the local sound speed, which is determined by the temperature and mean molecular weight of the stellar material. As we continue our descent through the radiative zone, we observe the gradual increase in temperature and density that characterizes the approach to the stellar core. The pressure rises to millions of times Earth's atmospheric pressure, while temperatures climb from the few million degrees at the convective boundary toward the tens of millions of degrees required for efficient nuclear fusion. These extreme conditions create an environment unlike anything found elsewhere in the universe. The equation of state-governing matter in the deep radiative zone begins to show departures from ideal gas behavior due to the extreme conditions. Radiation pressure becomes increasingly important relative to gas pressure, The high density begins to introduce quantum effects that will become even more pronounced as we approach the stellar core. Despite these complications, the basic physics of hydrostatic equilibrium and energy transport continues to determine the stellar structure. Near the base of the radiative zone, we begin to sense the proximity of the stellar core, where nuclear fusion processes generate the energy that ultimately powers all of Dubhe's observable properties. The temperature gradient steepens as we approach this nuclear furnace, and the composition may begin to show evidence of nuclear processing, helium ash from hydrogen burning, and traces of heavier elements from more advanced fusion processes. Standing at the threshold of Dubhe's nuclear core, we reflect on our journey through the radiative zone. We have witnessed the patient migration of energy through matter, observed the delicate balance of forces that maintain stellar stability, and appreciated the vast timescales involved in stellar energy transport. The radiative zone represents not just a passive conduit for energy, but a crucial component of stellar structure that helps regulate the star's evolution and maintain its stability over billions of years. As we descend toward the very heart of Dubhe, we approach the nuclear furnace that has powered this stellar giant for hundreds of millions of years and will continue to do so for hundreds of millions more. The stellar core represents the ultimate destination of our impossible journey, a region where matter exists under conditions so extreme that the very nature of atoms is transformed, and the fundamental forces of physics orchestrate the cosmic alchemy that creates elements heavier than hydrogen and helium. The boundary between Dubhe's radiative zone and its nuclear core is not sharply defined, but rather represents a gradual transition into regions where nuclear fusion becomes the dominant energy source. As we approach this realm, the temperature climbs steadily from the several million degrees of the inner radiative zone toward the tens of millions of degrees required for efficient thermonuclear reactions. The density simultaneously increases to several times that of solid metals, creating conditions that exist nowhere else in the natural universe except in stellar cores. The physics governing matter under these extreme conditions requires us to consider effects that are negligible under terrestrial circumstances. Quantum mechanics begins to play an increasingly important role as the high-density forces atomic nuclei close together. While the extreme temperatures provide the kinetic energy necessary to overcome the electromagnetic repulsion between positively charged nuclei, this combination of quantum tunneling and classical thermal motion enables the nuclear fusion reactions that make stellar energy production possible. The pressure at the approach to Dubhe's core reaches hundreds of billions of times Earth's atmospheric pressure. Under such conditions, matter exhibits behaviors that challenge our everyday understanding of physics. Despite densities that exceed those of the heaviest metals, the material remains gaseous due to the intense thermal motion of particles at temperatures exceeding 10 million Kelvin. The high temperatures ensure complete ionization, creating a plasma where atomic nuclei and electrons exist as separate, freely moving particles. Radiation pressure becomes increasingly dominant as we near the core, eventually approaching or exceeding the gas pressure from particle motion. This radiation pressure arises from the intense electromagnetic field created by the high-energy photons produced by nuclear reactions. The photons themselves carry momentum and exert pressure, contributing significantly to the outward force that balances gravitational compression in the stellar core. The chemical composition in the core region reflects Dubhe's nuclear history and current evolutionary state. As a K-type giant star, Dubhe has exhausted the hydrogen fuel in its central region and now burns hydrogen in a shell surrounding an inert core of helium ash. This helium core, the accumulated product of hundreds of millions of years of hydrogen fusion, continues to contract and heat up as additional helium is deposited on its surface by the hydrogen-burning shell. The core temperature of approximately 100 million Kelvin in the helium core is approaching, but has not yet reached the temperature required for helium fusion. Helium nuclei require much higher temperatures than hydrogen to overcome their greater electromagnetic repulsion, as they carry twice the electric charge of hydrogen nuclei. When the core temperature finally reaches about 200 million Kelvin, explosive helium burning will begin, marking a dramatic new phase in Dubhe's evolutionary development. The hydrogen-burning shell surrounding the helium core represents one of the most active nuclear regions in the star. Here, the CNO cycle dominates the fusion process, using carbon, nitrogen, and oxygen nuclei as catalysts to convert hydrogen into helium more efficiently than the proton-proton chain that powers less massive stars. This advanced burning process releases energy at a rate that maintains Dubhe's high luminosity as a giant star. The structure of the core region is determined by the competing effects of gravitational compression and nuclear energy production. The inert helium core continues to contract under its own gravity, converting gravitational potential energy into thermal energy that heats both the core and the surrounding hydrogen-burning shell. This contraction is a one-way process. Once hydrogen is exhausted in the core, it cannot be replenished, and the core must continue to evolve toward higher densities and temperatures. Neutrinos, ghostly particles produced by nuclear reactions, stream freely from the core region at nearly the speed of light. These nearly massless, weakly interacting particles provide the only direct observational probe of stellar nuclear processes, as they escape immediately from the core, without being absorbed or scattered by the overlying stellar material. The neutrino flux from Dubhe carries away a small but measurable fraction of the nuclear energy production. The magnetic field structure in the core region is complex and poorly understood. As direct observations are impossible, and theoretical models must rely on indirect evidence, the high conductivity of the plasma allows magnetic fields to become frozen in to the material, so that field lines move with the gas as it circulates or contracts. The core's magnetic field may play important roles in energy transport, mixing processes, and the eventual evolution toward helium ignition. Convective mixing can occur in localized regions around the hydrogen-burning shell, where the steep temperature gradient created by nuclear energy release can drive convective instability. These convective regions help to bring fresh hydrogen fuel into the burning zone, while carrying helium ash away, maintaining the nuclear reactions and contributing to the star's energy output. The size and behavior of these convective zones depend critically on the local temperature and opacity structure. The timescales associated with core evolution are vastly different from those of energy transport. While photons take hundreds of thousands of years to diffuse from the core to the surface, nuclear fuel consumption and core structure evolution occur on much longer timescales. The helium core grows slowly as hydrogen burning adds new material. The core contraction proceeds gradually over millions of years as gravitational energy is released. Stellar oscillations and acoustic waves can propagate through the core region, though their behavior is modified by the high density and temperature. These waves carry information about core conditions to the surface, where they can be detected through precise photometric observations. The study of stellar oscillations, or astroseismology, provides one of the few ways to probe the internal structure and composition of stellar cores. The approach to nuclear ignition conditions represents one of the most critical phases in stellar evolution. As the helium core continues to contract and heat up, it approaches the temperature and density threshold where helium fusion can begin. This process, known as the helium flash, in stars of intermediate mass, will dramatically alter Dubhe's structure and evolution when it eventually occurs. Quantum degeneracy effects begin to influence the behavior of electrons in the dense core material. As the density increases, electrons are forced into higher energy states due to the Pauli exclusion principle, creating a degeneracy pressure that partially supports the core against gravitational collapse. This quantum pressure will become increasingly important as the core continues to contract and may eventually dominate over thermal pressure in determining the core structure. The nuclear reaction network in the hydrogen-burning shell includes not only the primary CNO cycle, but also various side reactions and branching processes that produce trace amounts of heavier elements. These nuclear processes create isotopes of carbon, nitrogen, and oxygen that can be mixed to the surface by convection, potentially altering the observable surface composition of the star and providing clues about the interior nuclear processes, standing at the threshold of Dubhe's nuclear core. We prepare to witness the most fundamental processes that power stellar evolution. Here in this realm of extreme temperature and pressure, matter transcends its ordinary limitations and participates in the cosmic alchemy that has shaped the chemical evolution of the universe for billions of years. Our final descent will take us into the heart of nuclear fire, where the very elements that make up our bodies and our world are forged from the simplest building blocks of matter. At last, we arrive at the innermost sanctuary of Dubhe, the nuclear core, where temperatures soar beyond 100 million Kelvin and pressures reach hundreds of billions of times Earth's atmospheric pressure. This is the beating heart of the star, a realm where matter exists in its most extreme natural state and where the fundamental forces of physics orchestrate the magnificent process of stellar nucleosynthesis. Here, in conditions that dwarf any earthly experience, we witness the cosmic forge, where heavier elements are born from the ashes of primordial hydrogen and helium. The core of Dubhe consists primarily of helium for nuclei, the accumulated ash from hundreds of millions of years of hydrogen burning. This helium core has grown steadily throughout Dubhe's main sequence lifetime as the proton-proton chain, and CNO cycle converted hydrogen into helium in the central regions. Now, with hydrogen exhausted in the core, this inert helium mass continues to contract under its own gravity, slowly heating up as gravitational potential energy is converted to thermal energy. The temperature in Dubhe's core, while enormously hot by terrestrial standards, is still below the threshold required for helium fusion. Helium nuclei, with their +2 electric charge, experience much stronger electromagnetic repulsion than the single protons that participate in hydrogen burning. Overcoming this Coulomb barrier requires temperatures approaching 200 million Kelvin, roughly twice the current core temperature. Until this threshold is reached, the helium core remains nuclear inert, supported primarily by electron degeneracy pressure. Surrounding the inert helium core is a thin shell where hydrogen burning continues through the CNO cycle. This shell, perhaps only a few % of the stellar radius and thickness, generates the energy that maintains Dubhe's luminosity as a giant star. The nuclear reactions in this shell occur at a much higher rate per unit mass than the hydrogen burning that powered Dubhe during its main sequence phase due to the higher temperatures and densities that exist in this evolved stellar structure. The CNO cycle operates as a catalytic process where carbon, nitrogen, and oxygen nuclei facilitate the conversion of hydrogen to helium without being consumed in the net reaction. A carbon-12 nucleus captures a proton to become nitrogen-13. The energy released from these nuclear reactions follows Einstein's famous equation, E=mc, where the small difference in mass between the reactants and products is converted entirely to energy. Each helium nucleus produced has about 0.7% less mass than the 4 hydrogen nuclei from which it formed, and this mass deficit appears as kinetic energy of the reaction products and as electromagnetic radiation. The efficiency of this nuclear burning process far exceeds any chemical reaction, making it the ultimate source of energy for stars throughout their active lifetimes. The neutrinos produced by nuclear reactions in Dubhe's burning shell carry away approximately 2 to 3% of the total energy release. These nearly massless particles interact so weakly with matter that they escape immediately from the stellar interior, providing the only direct probe of nuclear processes deep within the star. The neutrino luminosity from Dubhe, while undetectable with current technology due to the star's distance, represents a significant energy loss that affects the star's overall energy budget and evolution. Electron degeneracy pressure plays an increasingly important role in supporting the helium core against gravitational collapse. As the density approaches several tons per cubic centimeter, the electrons are forced into higher and higher energy states due to the Pauli exclusion principle, which forbids multiple electrons from occupying the same quantum state. This quantum mechanical effect creates a pressure that depends on density rather than temperature, providing partial support for the core even as it continues to contract. The structure of Dubhe's core region exhibits a sharp density gradient at the boundary between the helium core and hydrogen-burning shell. The core density reaches several times that of solid platinum, while the shell density is more comparable to liquid water. This dramatic density contrast reflects the different physical processes operating in each region: quantum degeneracy in the core versus classical ideal gas behavior in the shell. Convective mixing occurs in localized regions around the hydrogen-burning shell, where the steep temperature gradient created by nuclear energy release drives convective instability. These narrow convective zones help to bring fresh hydrogen fuel into contact with the carbon, nitrogen, and oxygen catalysts, while carrying away the helium ash produced by nuclear burning. The efficiency of this mixing process affects both the nuclear burning rate and the growth rate of the helium core. The magnetic field structure in Dubhe's core is complex and potentially important for the star's long-term evolution. The high electrical conductivity of the plasma allows magnetic field lines to become frozen into the material, so that field evolution follows the motion and compression of the gas. Magnetic fields may influence convective mixing processes, energy transport, and the eventual ignition of helium burning when core conditions finally reach the required temperature. Trace amounts of elements heavier than helium begin to appear in the core region through various nuclear processes. The CNO cycle produces isotopes of carbon, nitrogen, and oxygen, while side reactions can create small quantities of neon, sodium, and magnesium. These heavier elements, though present in minute concentrations, can affect the stellar opacity and equation of state, potentially influencing the star's evolutionary path. The approaching helium flash represents the next major milestone in Dubhe's evolution. As the inert helium core continues to contract and heat up, it will eventually reach the temperature threshold where the triple alpha process can convert helium into carbon. This process requires 3 helium nuclei to combine nearly simultaneously, first forming the unstable beryllium-8 nucleus, which must capture another helium nucleus before decaying. The probability of this three-body reaction is extremely sensitive to temperature, leading to explosive helium ignition when the threshold is finally reached. The core rotation rate may differ significantly from the surface rotation due to the lack of strong coupling between the core and outer layers. Angular momentum conservation during the core contraction phase could lead to increased rotation rates in the central regions, potentially affecting the mixing processes and magnetic field generation. Differential rotation between core and envelope can also drive circulation patterns that influence chemical transport throughout the stellar interior. Stellar oscillations propagating through the core region carry information about the central conditions to the stellar surface, where they can be detected through precise photometry. The frequency spectrum of these oscillations depends on the density profile, temperature structure, and chemical composition of the core, providing astronomers with a seismic probe of stellar interior conditions. The study of these oscillations, astroseismology, represents one of the most powerful techniques for understanding stellar structure and evolution. The timescales for core evolution are determined by the nuclear fuel consumption rate and the core contraction timescale. The hydrogen-burning shell consumes fuel and deposits helium ash on the core surface over periods of millions of years, while the core contraction proceeds on the Kelvin-Helmholtz timescale of approximately 30 million years for a star of Dubhe's mass. These evolutionary timescales are long compared to human history, but brief compared to the total stellar lifetime. The quantum tunneling effects become crucial for nuclear reactions in the core region. As the thermal energies of the nuclei are insufficient to classically overcome the Coulomb barriers, the wave nature of matter allows nuclei to penetrate these energy barriers with small but finite probability, enabling nuclear fusion to occur at temperatures much lower than would be required for classical particle interactions. This quantum mechanical effect makes stellar nuclear burning possible and determines the temperature sensitivity of reaction rates. The energy transport in the immediate vicinity of the nuclear burning regions involves both radiative diffusion and convective mixing. The intense energy release in the hydrogen-burning shell creates steep temperature gradients that can drive local convection, while the more gradual heating in the helium core is transported primarily by radiation and conduction. The balance between these transport mechanisms affects the temperature distribution and nuclear burning rates throughout the core region. Standing in the nuclear heart of Dubhe, we witness the fundamental processes that power not only this star, but the entire universe of luminous matter. The nuclear reactions occurring around us have been creating and distributing heavier elements for billions of years, gradually enriching the interstellar medium with the carbon, oxygen, nitrogen, and other elements essential for rocky planets and biological life. We are observing the cosmic alchemy that makes our existence possible. The inexorable march toward helium ignition represents both an ending and a beginning in Dubhe's evolutionary story. The exhaustion of core hydrogen marked the end of the star's main sequence lifetime and the beginning of its giant phase. The eventual ignition of helium burning will mark another major transition, converting the inert helium core into an active nuclear furnace that will power the star through the next phase of its evolution toward even more advanced nuclear burning stages. Having reached the nuclear heart of Dubhe, Witness the processes that currently power this stellar giant, we now turn our attention to the future. The inevitable evolutionary path that will transform our gentle orange giant through several more spectacular phases before its final stellar retirement. The story of Dubhe's future is written in the language of nuclear physics and stellar structure. A slow but inexorable dance of expansion, contraction, nuclear ignition, and mass loss that will play out over hundreds of millions of years. The next major milestone in Dubhe's evolution will be the helium flash, dramatic event that will occur when the contracting helium core finally reaches the temperature threshold of approximately 200 million Kelvin required for helium fusion. This event, despite its name suggesting violence, will actually occur as a gradual heating and expansion of the core over a period of several years. The term flash refers to the timescale of nuclear processes rather than observable changes. As the energy release occurs deep within the star and takes thousands of years to reach the surface. When helium burning finally ignites through the triple alpha process, 3 helium nuclei will combine to form carbon-12 in a 2-step reaction that requires precise timing and favorable conditions. The first step produces the unstable beryllium-8 nucleus from 2 helium nuclei, which must then capture a 3rd helium nucleus before decaying with a half-life of only 10 to 16 seconds. This incredibly improbable reaction becomes possible only at the extreme temperatures and densities found in stellar cores. The onset of core helium burning will fundamentally alter Dubhe's internal structure and evolutionary path. The nuclear energy release in the core will halt the gravitational contraction that has been driving the star's evolution since the end of main sequence hydrogen burning. The star will settle into a new phase of nuclear equilibrium, burning helium in the core while continuing to burn hydrogen in the surrounding shell. This phase, known as the horizontal branch or red clump phase depending on the stellar mass, will last for several tens of millions of years. During core helium burning, Dubhe will likely experience a period of relative stability compared to its current rapid evolution as a red giant. The dual nuclear energy sources, helium fusion in the core and hydrogen fusion in the shell, will provide sufficient energy to maintain the star's luminosity, while preventing further dramatic structural changes. The surface temperature may increase slightly, causing Dubhe to appear somewhat bluer than its current orange color. Though it will remain cooler than main sequence stars of comparable mass, the nuclear reactions during helium burning will create progressively heavier elements through a series of alpha particle additions. Carbon-12 nuclei, produced by the triple alpha process, can capture additional helium nuclei to form oxygen-16, neon-20, and potentially magnesium-24. These reactions proceed more slowly than the initial carbon production, creating a core composition dominated by carbon and oxygen with smaller amounts of heavier elements. This mixture of nuclear ashes will determine the star's subsequent evolutionary path. The duration of core helium burning depends on the efficiency of the nuclear reactions and the mass of the helium core. For a star of Dubhe's mass, this phase will last approximately 20 to 50 million years. Much shorter than the several hundred million years of main sequence hydrogen burning. The shorter lifetime reflects both the smaller amount of helium fuel compared to the original hydrogen content and the higher nuclear burning rate required to maintain the star's elevated luminosity as a giant. As core helium becomes exhausted, Dubhe will face another evolutionary crisis similar to the end of core hydrogen burning. The nuclear fires in the core will begin to weaken, allowing gravity to again dominate and compress the now inert carbon-oxygen core. This compression will heat both the core and the surrounding shells, igniting helium burning in a shell around the carbon-oxygen core. While hydrogen burning continues in an outer shell, the star will then have 2 nuclear burning shells operating simultaneously. This double shell burning phase represents one of the most complex and dynamic periods in stellar evolution. The interaction between the 2 nuclear burning shells can create instabilities that lead to thermal pulses, periodic episodes where the helium burning shell experiences dramatic increases in nuclear burning rate. These pulses can temporarily disrupt the stellar structure and drive powerful convective episodes that mix nuclear products from the interior to the surface layers. During the thermal pulse phase, Dubhe will likely evolve into an asymptotic giant branch, Dubhe Star, becoming even larger and more luminous than during its current red giant phase. the stellar radius may expand to several hundred solar radii, making the star large enough to engulf the entire inner solar system if placed at the Sun's position. Despite this enormous size, the surface temperature will remain relatively cool, giving the star a deep red color and high infrared luminosity. The thermal pulses will also drive strong stellar winds that begin to strip away Dubhe's outer layers. These winds, accelerated by radiation pressure on dust grains forming in the cool stellar atmosphere, can remove substantial amounts of stellar material over relatively short periods. The mass loss rate during this phase can reach 10 to 5 to 10 to 4 solar masses per year, meaning that a significant fraction of the star's envelope will be expelled into space over the course of the AGB phase. The material expelled by Dubhe's stellar winds will enrich the surrounding interstellar medium with heavy elements forged in the stellar interior. Carbon and oxygen produced by helium burning, along with trace amounts of neon, magnesium, and other elements, will be distributed throughout the local galactic neighborhood. This stellar contribution to galactic chemical evolution represents one of the primary mechanisms by which stars return processed material to the interstellar medium for incorporation into future generations of stars and planets. The final fate of Dubhe's carbon-oxygen core will depend on whether it can ignite carbon fusion before losing too much mass through stellar winds. Stars with initial masses below approximately 8 to 10 solar masses generally do not achieve the core temperatures required for carbon burning and instead end their lives as white dwarf stars. Given Dubhe's current mass of about 2.2 solar masses, it will likely follow this path, gradually losing its envelope through stellar winds while the core contracts and heats up without reaching carbon ignition. As the stellar winds strip away the outer layers, they will eventually expose the hot, dense core to direct observation. The intense ultraviolet radiation from the exposed core will ionize the previously expelled material, creating a glowing shell of gas known as a planetary nebula. Despite its name, planetary nebulae have nothing to do with planet formation. They were named by early observers who noticed their circular, disc-like appearance in small telescopes. The planetary nebula phase will represent Dubhe's final moment of glory as an active star. The beautiful symmetrical shells of glowing gas can extend for several light-years around the central white dwarf, creating some of the most visually spectacular objects in the galaxy. The nebular shells will gradually expand and fade over periods of tens of thousands of years, eventually dispersing into the interstellar medium and leaving behind only the white dwarf remnant. The white dwarf that remains after Dubhe's envelope is expelled will be an incredibly dense object about the size of Earth, but containing roughly 60% of the original star's mass. This remnant will have a surface temperature initially exceeding 100,000 Kelvin, making it much hotter than any main sequence star, but its small size will limit its total luminosity. The white dwarf will slowly cool over billions of years, gradually fading from white to yellow to red, and eventually becoming a cold, dark cinder in space. The white dwarf phase represents true stellar death, the end of nuclear energy production, and the beginning of an inexorably long cooling process. Supported entirely by electron degeneracy pressure, the white dwarf will maintain a constant size while gradually radiating away its thermal energy. The cooling timescale is so long that no white dwarf in the current universe has yet cooled to become truly cold, as the universe is not old enough for this process to reach completion. Throughout this entire evolutionary sequence, from the current red giant phase through helium burning, thermal pulses, mass loss, planetary nebula formation, and final white dwarf cooling, Dubhe will contribute to the ongoing chemical evolution of the galaxy. The carbon, oxygen, nitrogen, and other elements forged in its nuclear furnaces will become part of the interstellar medium, available for incorporation into future generations of stars, planets, and potentially life itself. The total timescale for Dubhe's remaining evolution, from its current state to final white dwarf formation, will span several hundred million years. This represents a brief period compared to the star's main sequence lifetime, reflecting the rapid pace of stellar evolution once core hydrogen is exhausted. The various phases: core helium burning, thermal pulse, AGB evolution, mass loss, and planetary nebula formation, will each last for periods ranging from millions to tens of millions of years. Looking even further into the future, the white dwarf remnant of Dubhe will persist for trillions of years, slowly cooling in the darkness of space long after the The Sun has evolved through its own stellar life cycle, and the Milky Way galaxy has completed dozens of rotations around its center. In the far distant future, these white dwarf remnants may represent the last glowing embers of stellar activity in an aging universe where star formation has ceased and most normal matter has been locked up in stellar remnants. As we contemplate our imaginary journey from the surface of Dubhe back toward the realm of physical possibility, we must acknowledge the beautiful impossibility of what we have just experienced. Our gentle descent through the layers of this stellar giant, while scientifically accurate in its description of stellar physics, represents a voyage that no material object could ever survive. Understanding why this journey is impossible and what would really happen to any matter falling into a star deepens our appreciation for both the extreme nature of stellar interiors and the power of scientific imagination to explore realms beyond direct experience. The fundamental obstacle to our imagined journey lies in the extreme conditions that characterize stellar interiors. Long before reaching the nuclear core, any material object would be completely destroyed by temperatures, pressures, and radiation fields that exceed anything found elsewhere in the natural universe. The very atoms that comprise our hypothetical spacecraft would be ionized, then compressed, and finally transformed into plasma states that bear no resemblance to ordinary matter. The temperature gradient alone would prove catastrophic for any real object attempting this journey. Within the photosphere, temperatures reach thousands of degrees Kelvin, hot enough to vaporize any known material. In the convection zone, temperatures climb to millions of degrees, sufficient to completely ionize all atoms and strip away electrons from nuclei. By the time we reach the core, with temperatures exceeding 100 million Kelvin, even atomic nuclei would be moving at tremendous speeds and colliding with energies that can overcome the strong nuclear force. The pressure gradient presents equally insurmountable challenges. The atmospheric pressure on Earth's surface, which we consider normal, is utterly negligible compared to the pressures within Dubhe's interior. In the deep convection zone, pressures reach millions of times terrestrial atmospheric pressure, sufficient to compress any material to densities far exceeding those found in terrestrial experience. Near the core, pressures climb to billions of atmospheres, creating conditions where matter behaves according to exotic equations of state that have no analog in everyday life. The intense radiation field within Dubhe would prove lethal long before reaching the extreme temperature and pressure conditions of the deep interior. The photon density in stellar interiors is enormous, creating radiation pressures that can approach or exceed the gas pressure from particle motion. Any material object would be bombarded by high-energy photons carrying enough energy to break apart molecular bonds, ionize atoms, and ultimately disintegrate atomic nuclei through photodisintegration reactions. Gravitational forces during such a journey would create tidal effects that would tear apart any extended object long before it could reach the stellar surface. The difference in gravitational acceleration between the top and bottom of even a small spacecraft would create stretching forces that exceed the tensile strength of any material. These tidal forces increase dramatically as the object approaches the stellar center, ultimately becoming sufficient to disrupt matter at the atomic level. The timescales involved in such a hypothetical journey also present fundamental challenges to our imagined exploration. While we have described our descent as a leisurely voyage allowing detailed observation of stellar layers, the reality would be a catastrophic fall lasting only minutes or hours from the stellar surface to the center. The enormous gravitational acceleration near Dubhe's center would cause objects to reach velocities approaching significant fractions of the speed of light, making any detailed observation impossible even if the object could somehow survive the journey. Even if we could somehow imagine a magical material capable of surviving the temperature, pressure, and radiation conditions within Dubhe, the very presence of such an object would disturb the delicate hydrostatic equilibrium that maintains stellar structure. The stellar material is supported by a precise balance between gravitational compression and pressure from gas, radiation, and nuclear energy release. Introducing foreign matter would create density and pressure perturbations that could propagate throughout the star and potentially disrupt its stable structure. The nuclear environment in Dubhe's core presents additional challenges that transcend mere material survival. The intense flux of high-energy neutrons, protons, and other nuclear reaction products would subject any matter to nuclear transmutation processes that would fundamentally alter its atomic composition. What enters the core as one set of elements would be transformed into entirely different nuclear species through forced nuclear reactions. Driven by the extreme particle energies in the stellar center, magnetic field effects within the stellar interior would also profoundly affect any electrically conducting material attempting this journey. The strong magnetic fields threading through Dubhe's interior would induce enormous electric currents in any conducting object, leading to rapid heating and electromagnetic forces that could accelerate the object's destruction. The complex, time-varying magnetic field structure would create additional complications for any hypothetical spacecraft navigation or survival system. Despite these insurmountable physical obstacles, our imagined journey serves a crucial scientific purpose by allowing us to explore stellar physics in a visceral, experiential way that pure mathematical description cannot provide. By imagining ourselves present within these extreme environments, we gain intuitive understanding of the physical processes that govern stellar structure and evolution. This type of thought experiment represents a powerful tool for scientific education, an imagination allowing us to transcend the limitations of direct observation and explore regimes of nature that remain forever beyond human experience. The impossibility of our journey also highlights the remarkable achievement of theoretical astrophysics in mapping stellar interiors through mathematical models and physical reasoning alone. Without ever directly observing the interior of any star, astronomers have developed detailed understanding of stellar structure, nuclear processes, and evolutionary pathways through the application of fundamental physics principles. Our imagined descent through Dubhe follows paths charted by theoretical models that successfully predict observable stellar properties from first principles. Observational techniques such as astroseismology provide indirect confirmation of theoretical stellar structure models by detecting oscillations that propagate through stellar interiors. These stellar earthquakes carry information about density, temperature, and composition profiles from the core to the surface, allowing astronomers to probe stellar interiors with remarkable precision. The agreement between theoretical predictions and seismic observations validates our understanding of stellar physics and supports the accuracy of the interior conditions we have imagined during our impossible journey. Neutrino astronomy offers another window into stellar interiors. As these ghostly particles escape immediately from nuclear reaction zones and carry direct information about core conditions to external detectors, the detection of neutrinos from the Sun and other stars provides confirmation of nuclear fusion processes and core temperatures predicted by stellar models. Future neutrino telescopes may eventually detect neutrinos from stars like Dubhe, offering direct observational evidence for the nuclear processes we have imagined in its core. The impossibility of direct exploration makes stellar interiors one of the most remarkable achievements of human scientific imagination. Through careful application of physical laws, mathematical modeling, and indirect observational techniques, we have mapped regions of the universe that remain as inaccessible as the interior of a black hole, yet about which we possess detailed and accurate knowledge. Our gentle journey through Dubhe's interior, while physically impossible, represents a scientifically valid exploration of one of nature's most extreme and beautiful environments. As our impossible journey through Dubhe's interior draws toward its gentle conclusion, we turn our attention to the profound cultural and historical significance of this stellar giant in human civilization. Far beyond its role as a subject of astrophysical study, Dubhe has served for millennia as a celestial guide, a marker of seasons, and a source of wonder that has inspired countless generations of astronomers, navigators, poets, and dreamers. The star's cultural importance transcends its physical properties, weaving Dubhe into the very fabric of human relationship with the cosmos. The name Dubhe itself carries the weight of centuries of human observation and reverence. Derived from the Arabic phrase Thar al-Dub al-Akbar, meaning the back of the Great Bear. This designation reflects the sophisticated astronomical knowledge of medieval Islamic scholars who preserved and expanded upon ancient Greek constellation lore during the European Dark Ages. The Arabic astronomers saw in Dubhe not just a point of light, but a crucial anatomical feature of the celestial bear that prowls eternally around the northern pole of the sky. In the grand pattern of Ursa Major, Dubhe occupies a position of special significance as one of the two pointer stars that, together with Merak, guide observers to Polaris, the North Star. This navigational function has made Dubhe indispensable to human exploration and travel for countless centuries. Sailors crossing trackless oceans, merchants traversing desert caravan routes, and explorers venturing into unknown territories have all relied on Dubhe's steady presence to find their way home under starlit skies. The asterism we know as the Big Dipper, of which Dubhe forms the outer edge of the bowl, appears in the mythology and folklore of cultures around the world, though with widely varying interpretations. Native American traditions often see this pattern as a great bear being hunted across the sky, with the handle stars representing hunters in eternal pursuit. The blood of the wounded bear, according to some traditions, falls to earth each autumn, painting the leaves red and orange in a cosmic reminder of the celestial drama playing out overhead. European folklore has alternately viewed the Big Dipper as a wagon, a plow, or Charles's Wain chariot, reflecting the agricultural importance of these stars in marking seasonal changes. Farmers throughout history have used the orientation and position of the Big Dipper to determine planting and harvesting times, making Dubhe and its companions not merely celestial ornaments, but practical tools for survival and prosperity. In Hindu astronomy and mythology, the 7 bright stars of Ursa Major represent the Saptarishi, or 7 sages, great spiritual teachers who are said to guide humanity through cosmic cycles of creation and destruction. Dubhe, as one of these celestial sages, embodies wisdom and constancy. It's maintaining its position as a beacon of spiritual guidance, while the cosmos evolves around it. Chinese astronomy has long recognized Dubhe as part of the Northern Dipper, or Beidou, a constellation of enormous cultural and spiritual significance in Taoist tradition. The stars of Beidou were believed to control human destiny and the fate of nations, with Dubhe serving as one of the cosmic administrators overseeing earthly affairs. Chinese emperors claimed their authority derived from the mandate of heaven, symbolically represented by the circumpolar stars including Dubhe that never set below the horizon. The circumpolar nature of Dubhe and its companions, the fact that they never disappear below the horizon when viewed from northern latitudes, has contributed to their perception as eternal and unchanging in human culture. Unlike the seasonal constellations that rise and set with the turning year, the Big Dipper remains visible throughout the night and throughout the seasons. Though its orientation rotates around Polaris as Earth orbits the Sun, this constancy has made Dubhe a symbol of reliability and permanence in a universe that often seems chaotic and unpredictable. The development of scientific astronomy has revealed that our perception of Dubhe as eternal and unchanging is itself an illusion of human temporal perspective. The star is actually moving through space at approximately 20 kilometers per second relative to the Sun, participating in the grand rotation of the Milky Way galaxy over periods of tens of thousands of years. This motion will gradually alter the familiar pattern of the Big Dipper, eventually rendering our current constellation shapes unrecognizable to future civilizations. Modern light pollution in urban areas has tragically diminished the cultural connection between humans and stars like Dubhe. Many people living in cities today have never seen the Milky Way with their own eyes, or learned to navigate by the stars, representing a profound disconnection from one of humanity's oldest and most universal cultural traditions. The loss of dark skies represents not just an environmental problem, but a cultural tragedy that severs our connection to cosmic perspectives that have shaped human consciousness for millennia. Despite this urban disconnection, Dubhe and the Big Dipper remain among the most recognized star patterns in popular culture, appearing in everything from corporate logos to children's books. The familiar shape continues to evoke feelings of wonder and connection to the natural world, even among those who rarely have opportunity to observe it directly. This enduring cultural resonance testifies to the deep psychological importance of celestial patterns in human consciousness. Amateur astronomy has experienced a renaissance in recent decades, with many people rediscovering the joy of stargazing and learning to identify constellations like Ursa Major. Dubhe serves as an ideal starting point for beginning stargazers, being bright, easily identifiable, and visible throughout the year from northern latitudes. The star's role in teaching people to find Polaris makes it a gateway to deeper astronomical knowledge and appreciation. The scientific study of Dubhe itself has contributed to our understanding of stellar evolution and galactic structure. As one of the nearer giant stars, Dubhe provides an excellent laboratory for studying the physics of evolved stars and testing theoretical models of stellar structure. The star's brightness and proximity make it accessible to detailed spectroscopic analysis, yielding information about surface composition, atmospheric dynamics, and interior processes that inform our broader understanding of how stars like our Sun will eventually evolve. Dube's role as a standard candle for calibrating stellar distance measurements has contributed to our understanding of galactic scale and structure. By carefully measuring the star's parallax, proper motion, and radial velocity, astronomers can determine its precise position and motion through space, contributing to three-dimensional maps of stellar positions and velocities that reveal the structure and dynamics of our local galactic neighborhood. The continued cultural significance of Dube and other traditional constellation stars raises important questions about how humanity will maintain connection to cosmic perspectives as we become an increasingly technological and urban species. Educational efforts to preserve dark sky areas, promote astronomical literacy, and maintain cultural traditions of stargazing represent important investments in preserving humanity's cosmic heritage for future generations. In an age of space exploration and exoplanet discovery, stars like Dube remind us that our cosmic neighborhood extends far beyond the solar system, and that the universe contains countless worlds and environments beyond our current ability to explore directly. The same nuclear processes we have imagined in Dube's core operate in billions of other stars throughout the galaxy, creating the elements necessary for rocky planets and potentially biological life in stellar systems we can barely imagine. The light we see from Dube tonight began its journey toward Earth over a century ago. During the presidency of Theodore Roosevelt, in the early days of human-powered flight, this temporal connection across space reminds us that observation of stars is always observation of the past, and that the photons entering our eyes carry with them the history of distant worlds and times. When we look at Dube, we are literally seeing into the past and connecting across cosmic distances that dwarf any earthly separation. As we near the end of our gentle exploration of Dube, we must place this magnificent star within the larger context of cosmic evolution and galactic development. Dube is not merely an isolated stellar giant burning alone in space, but rather an integral participant in the grand narrative of universal development that began with the Big Bang and continues today through processes of stellar birth, evolution, death, and rebirth. Understanding Dube's role in this cosmic story illuminates how individual stars contribute to the ongoing chemical and structural evolution of galaxies, and ultimately to the conditions that make life possible throughout the universe. The story of Dube begins not with the star's own formation, but with the deaths of previous generations of stars that enriched the local interstellar medium with heavy elements necessary for Dube's formation. When the universe was young, only hydrogen and helium existed in significant quantities. It's created during the first few minutes after the Big Bang. The carbon, oxygen, nitrogen, and other heavier elements we find in Dube's atmosphere were forged in the nuclear furnaces of earlier stars and distributed through space by stellar winds and supernova explosions, creating the chemically enriched environment from which Dube eventually condensed. The molecular cloud that gave birth to Dube approximately 300 million years ago contained this accumulated stellar heritage, atoms of carbon forged in the cores of red giant stars, oxygen created by massive stars before their supernova explosions, and iron synthesized during the violent collapse and explosion of stellar cores. This chemical inheritance enabled Dube to form with the relatively high metallicity characteristic of younger stellar generations, affecting its opacity, evolution rate, and ultimate fate. During its main sequence lifetime, Dube has served as a stable nuclear furnace, converting hydrogen into helium and releasing energy that has illuminated its local neighborhood for hundreds of millions of years. This energy production represents Dube's primary contribution to galactic energetics, adding to the total luminosity of the Milky Way and participating in the complex energy budget that governs galactic structure and evolution. The star's luminosity has remained relatively constant throughout its main sequence phase, providing a steady energy source that could potentially support planetary systems and the complex chemistry necessary for biological processes. As an evolved giant star, Dube now participates in more advanced nuclear processes that create elements heavier than helium. The CNO cycle operating in its hydrogen-burning shell not only generates energy, but also serves as a cosmic laboratory for stellar nucleosynthesis, creating isotopes of carbon, nitrogen, and oxygen that will eventually be distributed throughout the galaxy. When Dubhe eventually reaches the helium burning phase, it will produce carbon and oxygen through alpha particle capture processes, adding to the galactic inventory of these biologically crucial elements. The stellar winds that currently flow from Dubhe's surface, though modest compared to those of more massive stars, contribute to the ongoing chemical enrichment of the interstellar medium. These winds carry processed material from the stellar interior into the surrounding space, where it can be incorporated into future generations of stars and planetary systems. The elements created in Dubhe's nuclear furnace may eventually become part of terrestrial planets orbiting stars yet to be born, potentially providing the raw materials for biological evolution in distant futures. Dubhe's gravitational influence extends beyond its immediate stellar neighborhood to participate in the larger dynamics of galactic structure. As part of the Milky Way's stellar population, Dubhe contributes to the collective gravitational field that maintains galactic structure and influences the orbits of gas clouds, star clusters, and other galactic components. The star's motion through space, carrying it around the galactic center once every 230 million years, helps to maintain the spiral density waves that create and maintain the galaxy's characteristic spiral arm structure. The location of Dubhe within the galactic disk places it in a region of active star formation and chemical evolution. Unlike stars in the galactic halo, which formed early in the galaxy's history from relatively metal-poor material, disk stars like Dubhe represent more recent stellar generations that have benefited from billions of years of galactic chemical evolution. This metallicity affects not only the star's internal structure and evolution, but also its potential for forming planetary systems with terrestrial worlds capable of supporting complex chemistry and potentially life. Dubhe's eventual evolution through the red giant branch, asymptotic giant branch, and planetary nebula phases will represent its most dramatic contribution to galactic chemical evolution during these final phases of stellar evolution. Thermal pulses and strong stellar winds will expel a significant fraction of the star's mass into space, enriching the interstellar medium with carbon, oxygen, and other heavy elements forged in the stellar interior. The planetary nebula phase will create a spectacular display visible across interstellar distances, while distributing processed stellar material throughout the local galactic neighborhood. The white dwarf remnant that will remain after Dubhe's envelope is expelled will continue to play a role in galactic evolution for billions of years to come. These stellar remnants serve as long-lived repositories of processed nuclear material, gradually cooling while maintaining their chemical composition essentially unchanged. White dwarfs also participate in some of the most energetic phenomena in the galaxy when they accrete material from companion stars, potentially leading to nova explosions that further distribute heavy elements throughout the interstellar medium. Dubhe's contribution to the galactic ecology extends beyond chemical enrichment to include energy injection into the interstellar medium through stellar winds, radiation pressure, and eventual mass ejection. These energy sources help to maintain the turbulent structure of interstellar gas clouds, preventing them from collapsing too rapidly under their own gravity and regulating the rate of star formation throughout the galaxy. This feedback process helps to maintain galactic structure and ensures that star formation continues over cosmic timescales rather than consuming all available material in a brief initial burst. The elements created in stars like Dubhe have been essential for the development of planetary systems capable of supporting life. Carbon enables the complex organic chemistry that underlies all known biological processes, while oxygen provides the basis for water and oxidative metabolism. Nitrogen is crucial for amino acids and nucleic acids, while heavier elements like iron, calcium, and phosphorus play essential roles in biological structures and processes. Without stellar nucleosynthesis and stars like Dubhe, the universe would remain a collection of hydrogen and helium gas, incapable of supporting the complex chemistry necessary for life. The timescales of stellar evolution and galactic chemical enrichment operate on scales vastly longer than human experience but remarkably brief compared to cosmic timescales. Dubhe's entire stellar lifetime, from formation to white dwarf cooling, spans approximately 1 billion years, roughly 1/10 the age of the universe itself. During this time, the galaxy will complete several rotations, star formation will continue in spiral arms and other active regions. And the overall chemical composition of the interstellar medium will continue to evolve through the contributions of Dubhe and countless other stars. Looking toward the far future, the elements created in Dubhe will persist long after the star itself has faded to invisibility. The carbon and oxygen nuclei forged in its nuclear furnace are essentially immortal, surviving the destruction of their parent star, and potentially being recycled through numerous future generations of stellar systems. These atoms may eventually become incorporated into terrestrial planets, organic molecules, or even living organisms in stellar systems that will not form for billions of years after Dubhe's demise. The study of stars like Dubhe provides crucial insights into the processes that govern galactic evolution and the development of cosmic structures on the largest scales. By understanding how individual stars form, evolve, and contribute to chemical enrichment, astronomers can construct models of galactic evolution that predict the changing chemical composition, star formation history, and ultimate fate of galaxies throughout the universe. Dubhe serves as both a representative example and a detailed case study of the stellar processes that shape cosmic evolution. In the context of searches for extraterrestrial life and habitable exoplanets, stars like Dubhe represent important laboratories for understanding the conditions necessary for biological evolution. The stable energy output during the main sequence phase, the production of heavy elements essential for terrestrial planet formation, and the gradual chemical enrichment of planetary systems all contribute to the potential habitability of worlds orbiting stars. Similar to Dubhe, understanding stellar evolution helps astronomers identify the most promising targets for searches for signs of life beyond our solar system. The philosophical implications of Dubhe's role in cosmic evolution extend far beyond astronomy and astrophysics. The star serves as a tangible connection between human existence and the cosmic processes that created the elements comprising our bodies and our world. When we observe Dubhe in the night sky, we are witnessing an active participant in the ongoing chemical evolution that makes our existence possible, creating a profound sense of connection to the universe at large. As our impossible voyage through the heart of Dubhe draws toward its gentle conclusion, we pause to reflect on the profound lessons and insights that have emerged from our stellar exploration. Our journey from the cold emptiness of interstellar space through the turbulent atmosphere of the churning convection zone, the patient, radiative interior, and finally into the nuclear furnace of the stellar core, has revealed not just the physical structure of a star, but the elegant interconnectedness of processes that govern cosmic evolution on the grandest scales. Perhaps the most striking lesson from our journey is the recognition that what appears from Earth as a simple point of orange light represents one of the most complex and dynamic systems in the natural universe. Dubhe is not merely a ball of glowing gas, but rather a carefully orchestrated symphony of nuclear physics, thermodynamics, fluid dynamics, and electromagnetic interactions, all balanced in delicate equilibrium over timescales that span hundreds of millions of years. The star represents a masterpiece of natural engineering, where every component from the surface granulation to the core nuclear reactions serves essential functions in maintaining stellar stability and evolution. Our exploration has also illuminated the profound patience that characterizes stellar processes. The energy we observe streaming from Dubhe's surface began its journey in the nuclear core hundreds of thousands of years ago, slowly diffusing outward through countless absorption and re-emission events, before finally escaping into space as the warm orange light that guides human navigation. This temporal perspective reminds us that stellar phenomena operate on timescales that dwarf human experience, yet somehow manage to maintain the stability and predictability that make them reliable celestial markers. The journey has revealed the fundamental unity underlying apparently diverse physical phenomena. The same nuclear processes that power Dubhe's luminosity also create the elements necessary for terrestrial planets and biological life. The same gravitational forces that maintain stellar structure also govern planetary orbits and galactic dynamics. The same electromagnetic radiation that provides stellar energy also enables the complex chemistry that underlies organic molecules and living systems. Our voyage through Dubhe has thus been a journey through the fundamental interconnectedness of cosmic processes. We have also gained appreciation for the crucial role that extreme conditions play in cosmic evolution. The temperatures and pressures within Dubhe's interior, while utterly hostile to any form of matter we recognize, are precisely what enables stellar nucleosynthesis and the creation of heavy elements. Without these extreme conditions, the universe would remain a sterile collection of hydrogen and helium, capable of forming the complex structures and chemical processes that characterize our cosmos. The hostile environment of stellar interiors thus represents not a failure of cosmic design, but rather an essential component of the processes that make complexity and life possible. Our exploration has demonstrated the power of scientific imagination to transcend the limitations of direct observation and experience. While we can never physically journey into a stellar interior, the combination of theoretical physics, observational astronomy, and mathematical modeling allows us to map these inaccessible realms with remarkable precision. The agreement between theoretical predictions and observational constraints provides confidence that our imagined journey accurately represents the conditions and processes operating within real stellar interiors. The impossibility of our journey has also highlighted the remarkable achievement represented by stellar astronomy. Through careful application of physical principles and ingenious observational techniques, astronomers have developed detailed understanding of stellar structure and evolution without ever directly sampling stellar material or visiting stellar interiors. This represents one of the great triumphs of human scientific reasoning, the ability to understand distant and inaccessible phenomena through the universal applicability of physical laws. Our journey through Dubhe has revealed the star as both an individual object with its own unique properties in evolutionary history, and as a representative example of stellar processes operating throughout the galaxy and universe. The nuclear reactions we witnessed in Dubhe's core are occurring simultaneously in billions of other stars, creating elements and energy that drive cosmic evolution on the largest scales. Understanding Dubhe thus provides insight into stellar populations, its galactic chemical evolution, and the cosmic conditions necessary for the development of complexity in life. The cultural and historical significance of Dubhe, which we explored alongside its physical properties, reminds us that scientific understanding represents only one dimension of humanity's relationship with the cosmos. Stars like Dubhe have served as navigational guides, seasonal markers, mythological characters, and sources of wonder throughout human history. The integration of scientific and cultural perspectives provides a richer, more complete understanding of our place in the cosmic order. Our exploration has also emphasized the dynamic nature of apparently stable stellar systems. While Dubhe appears unchanging from the perspective of human timescales, our journey revealed it to be a constantly evolving system undergoing continuous structural and compositional changes. The star's current configuration as an orange giant represents just one phase in a complex evolutionary sequence that began hundreds of millions of years ago and will continue for hundreds of millions more. This evolutionary perspective reminds us that stability and change are not opposites, but rather different aspects of the same underlying processes. The energy flows we encountered throughout our journey, from nuclear fusion in the core to convective transport to radiative diffusion to eventual escape at the surface, illustrate the fundamental importance of energy transport in cosmic systems. Stars represent elegant solutions to the problem of converting nuclear potential energy into electromagnetic radiation, maintaining themselves in stable configurations for billions of years while slowly consuming their nuclear fuel. The efficiency and stability of stellar energy production make stars the dominant energy sources in the universe and the foundation for all complex cosmic processes. Our journey has also revealed the essential role that feedback mechanisms play in maintaining stellar stability. The balance between gravitational compression and pressure support the regulation of nuclear burning rates. By temperature and density changes and the adjustment of energy transport mechanisms to maintain equilibrium, all demonstrate how stars naturally regulate their own structure and evolution. These feedback processes provide models for understanding stability and regulation in other complex systems throughout nature. Elemental composition we observe throughout Dubhe's interior tells the story not just of this individual star, but of galactic chemical evolution over billions of years. The hydrogen and helium that dominate the stellar composition are relics of the Big Bang, while the heavier elements represent contributions from previous generations of stars. Dubhe's nuclear processes are adding to this chemical heritage. creating new elements that will eventually be distributed throughout the galaxy to become part of future stellar and planetary systems. Our exploration has demonstrated how stellar physics connects the smallest scales of nuclear and atomic processes to the largest scales of galactic structure and cosmic evolution. The quantum mechanical processes that enable nuclear fusion in stellar cores ultimately power the luminosity that illuminates galaxies and provides energy for planetary systems. The nuclear products of stellar burning become the raw materials for terrestrial planet formation and biological evolution. Stars like Dubhe thus serve as crucial links in the chain of causation that connects the fundamental physics of matter to the emergence of complexity and life in the universe. As our peaceful journey through the stellar realm of Dubhe reaches its natural conclusion, we find ourselves forever changed by the experience of witnessing cosmic processes that operate far beyond the scale of human experience, yet intimately connect us to the deepest workings of the universe. We have traveled impossible distances through impossible conditions, guided by the gentle light of scientific understanding that illuminates even the most remote and extreme environments in the cosmos. Our voyage has been both an exploration of stellar physics and a meditation on humanity's place within the grand narrative of cosmic evolution. From the moment we first drifted away from Earth's familiar embrace into the vast emptiness of interstellar space, our journey has been characterized by a sense of wonder at the scales and processes that govern cosmic systems. The 123 light-year journey from our home world to Dubhe's glowing surface represents a distance so vast that light itself. Traveling at the ultimate cosmic speed limit requires over a century to bridge the gap between worlds. Yet this distance, enormous by human standards, represents merely a brief step within our local galactic neighborhood. Our gentle descent through Dubhe's atmospheric layers revealed the star not as a simple surface, but as a complex, multi-layered system where different physical processes dominate at different depths. The corona's million-degree plasma, the chromosphere's hydrogen glow, and the photosphere's granular convection cells each represent distinct environments shaped by the interplay of magnetic fields, radiation, and plasma dynamics. These atmospheric phenomena serve as our first introduction to the exotic conditions that characterize stellar interiors. The convection zone, with its massive currents of rising and falling plasma, provided our most dramatic encounter with stellar energy transport processes. Here we witnessed energy moving not as radiation or conduction, but as bulk motion of matter, with individual convection cells larger than entire planets, carrying thermal energy from the nuclear furnace below toward the stellar surface above. The magnetic dynamo processes operating in this turbulent environment generate the complex field structures that shape stellar atmospheres and drive stellar activity throughout the galaxy. Our patient passage through the radiative zone revealed one of the most remarkable aspects of stellar physics: the million-year journey that photons must complete to carry energy from the stellar core to the surface. In this stable, stratified environment, we observed the slow diffusion of electromagnetic radiation through matter so dense that photons travel only centimeters between absorption and re-emission events. The ancient light surrounding us in this zone began its journey toward the surface. When early humans were first developing complex tools and language, the nuclear core, the ultimate destination of our impossible voyage, provided direct witness to the cosmic alchemy that creates elements heavier than hydrogen and helium. Here, in conditions of temperature and pressure that exist nowhere else in the natural universe, we observed the nuclear processes that have been shaping galactic chemical evolution for billions of years. The CNO cycle operating in Dubhe's hydrogen-burning shell represents stellar nucleosynthesis at work, creating the carbon, nitrogen, and oxygen that make complex chemistry and biological life possible. Throughout our journey, we have been accompanied by the knowledge that our exploration, while scientifically accurate, represents an impossible dream that no material object could ever realize. The extreme conditions within stellar interiors would instantly destroy any form of matter we know, yet through scientific understanding and imagination, we have been able to map these inaccessible realms with precision and confidence. Our voyage thus represents both a triumph of human scientific reasoning and a testament to the power of imagination to transcend physical limitations. The cultural and historical significance of Dubhe, which we explored alongside its physical properties, reminds us that stars exist not merely as astrophysical objects, but as integral parts of human culture and consciousness. For thousands of years, Dubhe has served as a navigational guide, helping travelers find their way across trackless oceans and endless deserts. The star has witnessed the rise and fall of civilizations, the development of scientific understanding, and humanity's gradual recognition of our place within the cosmic order. Our exploration of Dubhe's evolutionary future revealed the star as a dynamic system undergoing continuous change over timescales that dwarf human history. The approaching helium flashed the eventual evolution through thermal pulse phases, the formation of a planetary nebula, and the final cooling as a white dwarf represent milestones in a stellar life cycle that connects Dubhe to the ongoing chemical evolution of the galaxy. The elements forged in Dubhe's nuclear furnace will persist long after the star itself has faded, potentially becoming part of future planetary systems and perhaps even future forms of life. The broader cosmic context within which Dubhe operates has revealed the star as both an individual object and a representative participant in galactic evolution. The nuclear processes we observed in Dubhe's interior are occurring simultaneously in billions of other stars throughout the Milky Way and beyond, collectively driving the chemical enrichment that makes complex cosmic structures possible. Understanding Dubhe thus provides insight into stellar populations, galactic dynamics, and the cosmic conditions that have enabled the emergence of complexity and life throughout the universe. As we reflect on our gentle journey, we recognize that the impossibility of direct stellar exploration makes stars like Dubhe among the most remarkable achievements of human scientific understanding. Through careful observation, theoretical reasoning, and mathematical modeling, astronomers have developed detailed knowledge of stellar interiors that remain as inaccessible as the event horizon of a black hole. Our imagined voyage follows paths charted entirely through scientific inference and reasoning, yet validated by countless observational confirmations of theoretical predictions. The peaceful nature of our exploration, approaching even the most extreme stellar conditions with gentle wonder rather than fear or violence, reflects the fundamentally benign character of scientific inquiry. Through science, we can explore realms of temperature, pressure, and energy density that would instantly annihilate any material observer. Yet we approach these extreme conditions not as threats, but as opportunities to understand the fundamental processes that govern cosmic evolution and make our existence possible. The energy flows we trace throughout our journey, from nuclear fusion in the core through convective and radiative transport to eventual escape as electromagnetic radiation, illustrate the fundamental role that stars play as cosmic energy processors. Dubhe converts nuclear potential energy into the electromagnetic radiation that illuminates its local environment, participates in galactic energy budgets, and potentially provides energy for any planetary systems that may orbit within its gravitational influence. Stars represent nature's most efficient and long-lived energy conversion systems, operating reliably for billions of years while slowly consuming their nuclear fuel. The elements we encountered throughout Dubhe's interior carry with them the history of cosmic chemical evolution extending back to the Big Bang and forward to distant futures we can barely imagine. The hydrogen and helium that dominate Dubhe's composition are relics of the universe's first few minutes, while the heavier elements represent gifts from previous generations of stars that lived, evolved, and died before Dubhe ever formed. The nuclear processes operating in Dubhe today continue this ancient tradition of cosmic alchemy, creating new elements that will eventually enrich future stellar and planetary systems. Our journey has also revealed the profound interconnectedness that characterizes cosmic systems at all scales. The same physical laws that govern nuclear reactions in stellar cores also determine the structure of atoms, the chemistry of biological molecules, and the dynamics of galactic systems. The elements created in stellar nucleosynthesis provide the raw materials for terrestrial planet formation, atmospheric evolution, and biological processes. Stars like Dubhe thus serve as crucial links connecting the physics of matter to the emergence of complexity, life, and consciousness throughout the universe. As we reach the end of our gentle journey through the heart of Dubhe, we have discovered that even the most extreme and seemingly hostile environments in the universe operate according to principles of elegant balance and patient process. Like ancient light finally reaching our eyes after eons of travel through stellar matter, the knowledge we have gathered on this impossible voyage will continue to illuminate our understanding of cosmic processes and our place within them. The nuclear fires we have witnessed in Dubhe's core burn not with destructive fury, but with the gentle persistence that creates elements, powers galactic evolution, and makes life possible throughout the cosmos. The star's patient conversion of hydrogen into helium, operating steadily for hundreds of millions of years, represents one of nature's most fundamental and benevolent processes. Rest well tonight, knowing that somewhere in the darkness above us Dubhe continues its ancient stellar dance, creating elements for worlds yet to be born, and maintaining the cosmic processes that connect us to the deepest workings of the universe. The warm orange light that has guided human travelers for countless centuries carries within it the story of stellar birth, evolution, and the patient alchemy that makes our existence possible. May the gentle mysteries we have explored together drift with you into peaceful sleep, carrying dreams of cosmic wonder, and the profound beauty that emerges from understanding our place within the infinite tapestry of stars. Good night from Sleepy Scientist Stories.